Okay, hey everybody. This problem, 222 from, forget which book, Incorpora Heat and Mass Transfer, the 2007 version. What we have right here is a nuclear fuel rod that's generating energy at some constant steady state rate. This is the equation for the temperature gradient, or the temperature throughout the cylinder. And then we have all these other conditions moving on through here. This is the constants that go into this equation, and the fuel rod properties. And then we know we have heat generation, this, which is a flux, basically, from volume. It's kind of flux, but the heat generation, Q dot, is watts per meter cubed. So how much is generated per volume? So we're going to find out this first part, the rate of heat transfer per unit length of the rod at R equal to 0 and R equal to 25 millimeters. Okay, so clear it up. So here's a basic drawing, and I took TR and I subbed in the values of A and B for it, just like this. So you can see that right off the bat, and then here are the properties. We know that the Q is actually coming, we have a Q dot in here, and we're trying to find the Q flux. I mislabeled that. Q flux. So flux throughout this outer surface right here. This is the surface where all the heat is coming from. So the equation that we're going to use is the Q heat transfer rate is negative K times the area of the rod times the partial of T with respect partial to R. And this is from the universal heat equation, which you can see in chapter 2. But so what we're going to do is we're going to go ahead and find area. Area is equal to 2 pi r times L. So the circumference times the length of the pipe. So subbing that in here, we're going to end up with QR is equal to negative K 2 pi r L of delta T over delta R. Just like that. But we're looking for the heat flux per unit length. So we're going to go ahead and divide this per unit length. Well, this is per unit length. I'm just going to say it. In order to do that, you actually have to divide by the length, so you end up with negative K of 2 pi R. The L's cancel because we just divided this by R. Partial of T, partial of R. Just like that. My partial kind of looks like 2 myself. I'm sorry. Okay. And this is a 2. Like that. So, excuse me. We need delta T with respect to R. Well, we have the temperature equation up here. So in order to get the partial of T with respect to R, we just go ahead and take the derivative of this equation with respect to R. So if you go ahead and do that, then partial of T with respect to partial of R is going to equal negative 2. I'm going to bring the negative out, the negative up here out. Take the derivative of R squared, negative 2, of 4.167 times 10 to the 5th R. And that's our partial of T, partial of R. So now we can just go ahead and straight up solve for the radius equal to 0. Well, since the radius is equal to 0, there's no real volume to be generating any heat. So basically, you know that the Q generation or the Q flux, or however you want to look at it, it's all going to equal to 0 because there's basically no material. So Q of 0 is equal to 0. So that's the answer to your first part. That's for part A. Or the first half. That's not part A. We're in part A. But then moving on to I'm actually going to go ahead and calculate this here real quick. This is going to be equal to negative 0.208 times 10 to the 5th Kelvin per meter. So the change in temperature is you change radius. So moving on and actually calculating R equal to 0.025 meters, 25 millimeters. So Q of R, we're using this equation up here, is equal to negative 30 watts per meter Kelvin times 2 pi times R. Hang on, let me make sure I get this all straight here for you. Okay, yes, we're okay. 0.025 meters. And then this is all calculated. So we'll check this. Oh, this is at R equal to 0.025 up here. So at the radius, this is calculated for the radius. Or you can take this value and you can bring it down here and then put in the radius that you want. But I calculated it up here before when I last worked this problem. Sorry. So this is going to be times negative 0.208 times 10 to the 5th Kelvin per meter. And you find out that this will equal a value of 0.980 times 10 to the 5th watts per meter. And this is your Q at 25 millimeters. Squeezing a lot of stuff in there, I'm sorry. This is your final answer. So you just go up, you take the basic equation, you find this by taking the partial derivative of that, and then you sub all the values in and you solve for Q dot. If we're using Q originally, you have to divide by the length in order to get the flux per unit length, and you have this final answer right here anyway. Pencil ran out of lead. Okay, and that's all it goes. Next video, what we'll do is solve part B where it's an unsteady problem.